Do I want to do 38? Let's see. No, we're not doing 38 until we do some other ones first.
47.
Okay, you've done. Okay, I'm gonna do 47. You did all of these fine? You did all the ones leading up to it? Okay, so what's your first step? What's the best thing you should do first?
Sketch the graph.
You're trying to find the region enclosed by these two. Y equals negative x plus 1. So, your first goal is to make a picture. Inside the steps, to reach that goal, you're going to do many of the things you guys just said all at once. But first thing is making a graph. So let's do that first. So then how do we go about graphing this right here? What do I need to do?
You can isolate y.
Yeah, you guys really like to make sure you isolate y. And actually a plus. Let's just finish. We could, but we're going to do it this way because this is the way we graph functions. So it's going to be the square root of x all over the square root of 2. We do the square root of x over 2. So when x is 0, oh, and it's plus or minus, right? So what's this going to look like? It's going. What point do you know it's going to go through? It's going to go through the origin. Is it going to go to the right or to the left? To the right, and it's going to be a square root function, so it kind of looks like this, like that. So do you see the region that it encloses? Yeah, the region that it encloses is right here. So when you look at this, you have to make a choice. Are you going to integrate with respect to x, or are you going to integrate with respect to y? Integrate with respect to y, because if you do it with respect to x, you run into that same problem we ran into 2 days ago. You have to break it into 2 integrals, and it's not going to be as nice as doing 1 integral, and your single integral, just the pieces will be nicer. So, subtract the blue 2y squared. We actually have it already, right? It's already isolated, 2y squared. There it is. And then, what's the only thing that's missing at this point? Limits of integration, which you find by calculating the points of intersection. I don't know, do you need the x values or the y values? Y. We're y. We're y. We're what? Yeah, you hope it's factorable, right? So what do you end up with? 2y, y, and what do you end up with? I don't know. Plus 1 and minus 1, like that? Is that correct? I think so. So y is equal to negative a half or excuse me, 1 half or negative 1. It kind of makes sense because the bottom looks like it's farther down. So what do you put here? You put the lower limit there. So what goes there? Negative 1 there and 1 half there. And then you evaluate this integral. Is that a rather straightforward integral? Yeah, you have to be a little careful. I'll tell you what the answer is. It is. Make a picture. So how do you go about making a picture of this? There's 2 different ways in which you can make a picture. What's the first way you can make a picture? Yes, with your calculator. Let's just graph it with the calculator. See what it looks. So where should we zoom in? I'm sorry. So let's just zoom box. Let's see, what's the window? So how about negative 1.5 to 1.5, and then 1.5 to. Yeah, it's not going to change much, I guess. Might warp it. Negative 1.5 to 1.5. Let's just graph this and see what happens. Huh, it's fitting on. That's nice. You see the curve, and then boom, there it is. So do we have a region? Do we have an enclosed region? What's nice about, how many pieces to the enclosed region are there? What's nice about those 2 pieces? They're equal to each other. Yeah, you can say that. That's fine. You don't have to really do it. And what's the upper function going to be? You already know it. Sine of pi x. Oh, and I'm not even writing it correctly. Sine of pi x divided by 2. It's a terrible pi. I don't know. And what are we subtracting from it? X dx. Now, how do you integrate that? What do you have to use? Just use u substitution. You don't really care about the negative x. You care about what's going on right here, correct? So you can just, before you do u substitution, you could rewrite it as the integral from 0 to 1 of sine of pi x divided by 2 minus the integral from 0 to 1 of x dx. The one on the right is pretty easy, but the other one is going to be u equals what? Pi x over 2. So du is going to be pi over 2 what? dx. Oh, there's a dx here, sorry, dx. So dx is equal to 2 over pi du. Now we just need to change the upper and lower limits of integration here. U equals pi x over 2, so you plug in 0, what do you get? 0. Plug in 1, what do you get? Pi over 2. And then you get sine of u times what? T pi times, well, 2 over pi times that, right. So then you end up with 2 over pi, integral of 0 to pi over 2 of sine of u du, and we do not have to substitute back for x because we've already changed the limits of integration. We changed it from x values to u values. So now we can just integrate this flat out and end up with 2 over pi times, what's the integral of sine? So I'll make it negative on the outside. Is that okay? From 0 to pi over 2. And that's going to be equal to negative 2 over pi. What's cosine of pi over 2? 0 minus what's cosine of 0? What is it? 1, exactly. So you end up with 2 over pi. So you end up with 2 over pi, but then you just have you have to do the other side over here. From 0 to 1, which is just going to be what? Negative 1/2. So it's this minus a half. How confident are we in that answer? Yes. You had a question, Coop? Does the what? I have the answer to all of them.
Okay, I figured out like how would you know?
I have the answer book. But you guys you're free to come in and look at whenever you want. I don't care. Okay. Okay, so now let's go to beyond 26, and I'm not going to do them all, but I'll do some of them. What do you want to do? 47. We have a bid for 47. Yeah. Ooh, that's a good one. You want to do 47?
Yeah.
It's a cool one. My D block class didn't ask about this one. You know what we did yesterday in D block? I hadn't done it. I'd never done it before. I hadn't done it as a teacher before. You know what we proved in class? The area of a circle is pi r squared. We proved it. It's really cool.
Isn't there something with the circumference or something you can take a string around a circle and
we used calculus. We used integral calculus is what we used.
Mr. Ralston way back now too.
Yeah.
In like my freshman year, showed us that like the circumference equals 2 pi r.
Yeah.
So there's something about this, I don't know.
Yeah, there's something.
The
there's more than one way. There's more than one way, sure. But there's a cool calculus way, which actually you guys aren't far from understanding, which is cool. Okay, find the values of C such that the area of the region enclosed by the parabolas is 576. So what kind of so C is a constant, you understand that?
Yeah.
What type of parabola is this? Facing up, yeah, that's good. What's this one? Facing down, okay. So what are the commonality? What's the commonality between, if you had to graph it, this, you don't know what C is, but you can make a guess.
You know it's going to be like 2 interlocking.
It's going to be symmetric, thank you. That's what I really wanted you to say right there, good. Okay, now it's recording again. There's been some dead space in the video, whatever. You know, one of them's facing up and one of them's facing down. What's the similarity between these two? They're going to have the same what?
No, they're
the same, the intercept, yeah, the X-intercepts, right? What are they going to be when X is equal to C or negative C? What do you plug in for X to make this 0? C and negative C. What do you plug in for X to make this 0? C and negative C. So if you think about it like this, if this is C, if that's negative C and this is C, one parabola is going to go like this. What's the other parabola going to do? The exact opposite. It's going to start, like here. It's going to go in a better curve than that, but. And I just zoomed out again. So there's your enclosed region. So you write an integral. Is it going to be in terms of X or Y? X. Is the upper one the blue one or the green one? Blue. So what are you integrating from and to? What's the left bound? Negative C. And what's the upper bound? The right bound, right? So the upper one is the blue one, and that's going to be C squared minus X squared. Careful. And what are you subtracting? Minus C squared. Dx. Yeah, but then you just have to take half of it, sure. I'm just going to set it equal to 576. So you do, you mean like just do one quadrant?
No, do like C squared minus X squared.
Then leave it off? Yeah, that's what I mean by a quadrant. Cooper, that's what I mean by a quadrant. What I'm saying is, if you wanted to, you're absolutely right. You could just focus on this right here.
Yeah, but I was saying negative. You could quadruple it.
You could just quadruple it. So yes, so let's go with that. Fine, we could totally go with that. So we could say that since we have symmetry across the x-axis and the y-axis, what could we say? We could just say that we're looking at 4 times, it's better than you think, it's 4 times 0 to c. What's the upper function? C squared minus X squared. What's the lower function if we just have, minus 0, right? dx. Is that a little easier? Yeah. But, yeah, it's much easier. What does this equal? 576. That equals 576. So, yeah, that's easier. That's a great observation to make. So let's just go with it because we made the observation. That's fine. So now you're looking at the integral from 0 to c of c squared minus x squared dx is equal to 576 over 4. Try solving that now. Go. So let's try it. We can do this. That's fine. What's 576 divided by 4? Anybody? 144. You do the integral, you get c squared x minus 1/3 x cubed from 0 to c. So you plug in 3 for what? X, right? 3 for x. Do you see that, right? So what do you end up with? 3c 0 to c. I'm sorry. 0 to c. That is my fault completely. C cubed minus 1/3 c cubed has to equal what? Which is 144, right? So that's 2/3 c cubed is 144. So c cubed is equal to 144 times 3 over, which is what? 216. 1/3, 1 minus 1/3. So c is equal to 6. We're going to transition to 3 dimensions, and we're going to do that as follows. We have looked at one of the first integrals we looked at was the area under the curve of y equals x squared from 0 to 1. We looked at it from 0 all the way to 1. So we looked at this region right there, 2-dimensional area. We added up an infinite number of what in order to calculate that? Rectangles, right. Okay, so one of those rectangles might be, let's say this was one of those rectangles right there. And how many of those rectangles did we add up? Well, we created a formula for an infinite number of them, well, as n goes to infinity, and then that limit would be the actual area. What we're going to do now is start rotating those rectangles. What I mean by that is this. So instead of having just a 2-dimensional shape, it'll pop out a little bit. You're going to have a mirror image of the function like this, and then you'll have a mirror of this right here. It's the same rectangle rotated down. My scale is not perfect. And you're going to rotate it. So it's going to pop out of, it's going to rotate this way and rotate there as well. So here's the edge of this disk now that you have. Can you kind of see the disk I'm trying to draw? Kind of see it? To rotate it around. So you had this slice and it rotated like this. So what is this shape right here? What is that? It's kind of a really short cylinder. It's a disk. It's a really short cylinder. Does everybody see what we're doing there? So if I had, let's just say I had a cylinder. Let's just say I had one right here. So I had it on its side like this. This is the shape you're looking at right there. How do you find the volume of a cylinder? Okay, you need the radius. So r is right there. And let's call that h. So it's going to be what? Pi r squared h. Okay. So the difference in orientation here is that, see these two disks right here? There's one right there, and there's one right there. If you're looking at that disk, here's the height right here. What do you think we're going to call that height? Nope. What do you think that is right there? It's going to be very, 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 very small, right? Because dx. This is going to be known as dx, an infinitesimal change in x. Everybody okay with that? Where's the radius? The radius goes from here to here, to the x-axis. So if this is the function y equals f of x, what's the radius now? Radius is f of x, the height. The radius is f of x. If you're at this point right here, the radius of this disk is going to be the distance from the function to the x-axis. What is the distance from the function to the x-axis? That is f of x. So if you wanted the volume of that specific disk, you're talking about pi times the radius f of x squared times what? dx. That right there is the volume of one washer. Well, a washer if there's a hole in it. I'm going to say washer a whole lot because think of it as a washer with no hole in it, okay? So it's just a disk.
Like a battery.
Little tiny ones, yeah, exactly, tiny flat. So are you okay with believing that that's the volume of that disk?
Yeah.
So you're going to add up a whole lot of them, right? You're going to add up a ton of them. In this case, if we wanted to rotate y equals, let's say that was y equals, let's change it to something. Let's say it was equal to what? X squared. And we're going from 0 to 1, just to make it nice. We are going to evaluate, I'm going to show you what we're going to evaluate. We're going to evaluate the integral from what to what? 0 to 1 of pi times f of x squared dx. But in this case, what is f of x? X squared. I'm looking for the, you need to be an x value. So it's going to be the integral from 0 to 1 of pi times x squared dx. So what's that going to be? You can factor out the pi, 0 to 1 of x to the, and that's equal to pi times 1/5 from, which is equal to just pi over 5. We just found our first volume. We just found our first volume. Rotational solids are really, really common. They will happen, you're guaranteed to see some rotational rotational solids on the AP exam. Absolutely guaranteed to see in multiple choice. Very likely it's possible on the free response. The only limiter to the free response is only 6 questions, so possibly, but it's very common, very common. So let's generalize this a little bit. So let's say I asked you, right here, let's do this one right here. I'm going to draw a arc right here. Here we go. And we're going to say that that's equal to y equals the square root of 1 minus x squared. That's also known as the upper half of a circle of radius what? 1. So if the radius was r instead, if the radius was r, what would change about this equation? It would, not the x turns into the r, it would be a r squared minus x squared. That's the only thing that changes. Because what's the equation for what's this equation for a circle? X squared plus y squared is equal to r squared. So what does y squared equal? R squared minus x squared, so y is equal to the square root of, so it's plus or minus, but we only want the upper half, okay? So here's what we're going to do. We're going to take that arc, and we're going to look at that shape if you rotated it around the x-axis. We're going to rotate this around the x-axis. We're going to what shape is it going to make? No, not an oval. A circle. It's going to make a sphere. It's going to make a sphere. It's a circle. It's the upper half of a circle, so if you rotate it, what are you going to get? A sphere. So what you want to get good at, and this is what you're going to practice, is you absolutely need to actually draw one of these, and stop eating because you didn't ask. Thank you. You're going to rotate this down. Ah, that's a really poor arc right there. It's going to rotate down. You need to get good at drawing these. So do you understand how that's the upper and lower part, like the shadow right there? The key, here's the key to drawing in 3 dimensions. Too many lines will kill it. Too many lines will kill it. I'm drawing it with too many lines here just to emphasize that there is a little bit of thickness here. There's a little bit. So theoretically, if you want to continue drawing it this way, draw that one, and then that one, and then it goes to the back. And it goes to the back. So do you kind of see that slice I'm trying to draw right there, popping out at you? It's coming out at you at least, right? You can do that with just single lines if you want to, but there is your one slice. Draw your slice. Are we going to integrate with respect to x or y? X. The little tiny thicknesses are all x pieces, so we're integrating with respect to x. Write dx like this. Since we're rotating and these are disks, what constant is always going to be out front, in front of the integral? Pi. Pi is going to sit out there. It's pi r squared. That's what we're working with now. Pi r squared. What's the lower limit of integration? What's our leftmost x value? What's our leftmost x value? No, the radius is r now. So what is it going to be? Negative r. So we're going from negative r to positive r. And now we just need the radius. The radius is the distance from any point to the x-axis. So that's just going to be the output. What's the output of this function? Root what? Root r squared minus x squared, right there. Root r squared minus x squared. Question, let's say I'm at this point right here. That point is going to be x comma what? No, the square root of, yes, y, r squared minus x squared. So the radius is the distance from here to here. What is that green distance? Griffin? That green distance is this right there. So that marches down right there, and why do you square it? The area of a circle is
Yeah,
pi r squared. Now, what's the really nice thing? We're squaring a square root, so what happens? It cancels. So you're left with pi times the integral from negative r to r of minus x squared dx. What is r? It's a constant, right?
Yeah.
So if we integrate r squared with respect to x, what do you end up with? No, you're integrating, not differentiating. R squared x minus 1/3 x cubed from negative r to r. So now we just have to be careful here. We have pi times, what, r cubed minus 1/3 r cubed minus, now we're plugging in the negative r. Be very careful with your negatives. What do you end up with? Minus negative r cubed plus 1/3 r cubed. So you have pi times 2/3 r cubed minus negative, I'm just doing it in pieces here, 2/3 r cubed. So how many r cubes do you have? Pi times 4/3 r cubed. You ever seen this before? 4/3 pi r cubed. There it is. There's the volume of a sphere. This is the volume of a sphere. Volume of a sphere. We just proved the volume of a sphere. Here's the caveat to this, though. The caveat, though, is what is this method entirely reliant on? What formula is this method entirely reliant on? Pi r squared. Without pi r squared, we can't go anywhere. Remember at the beginning of class I mentioned we did something really cool in BC calculus? What did we prove in BC calculus? That the area of a circle is pi r squared. It's not trivial. It's not trivial. Here's why it's not trivial. Actually, I can explain to you why it's not trivial just for a thing that you realized you had to do. You do it in terms of y, exactly. Why'd you know that? Well, you drew your slice and you realized this thickness, is this a dx? No. No, what is it? So everything has to be in terms of y, exactly.